My name is Geppi Parziale and I'm a machine learning engineer here at Apple. Today, I want to walk you through the journey of building an app that uses machine learning to solve a problem that will usually require an expert to perform some very specialized work. This journey gives me the opportunity to show you how to add open source machine learning models to your apps and create fantastic new experiences. During the journey, I will also highlight a few of the many tools, frameworks, and APIs available for you in the Apple development ecosystem to build apps using machine learning. When building an app, you, the developer, go through a series of decisions that hopefully will bring the best experience to your user. And this is also true when adding machine learning functionality to applications. During the development, you could ask, should I use machine learning to build this feature? How can I get machine learning model? How do I make that model compatible with Apple platforms? Will that model work for my specific use case? Does it run on the Apple Neural Engine? So let's take this journey together. I want to build an app that allows me to add realistic colors to my family black and white photos that I found in an old box in my basement. Of course, a professional photographer could do this with some manual work, spending some time in a photo editing tool. Instead, what if I want to automate this process and apply the colorization in just a few seconds? This seems to be a perfect task for machine learning. Apple offers a tremendous amount of frameworks and tools that can help you build and integrate ML functionality in your apps. They provide everything from data processing to model training and inference. For this journey, I'm going to use a few of them. But remember, you have many to choose from, depending on the specific machine learning task you are developing. The process I use when developing a machine learning feature in my apps goes through a set of stages. First, I search for the right machine learning model in either scientific publication or specialized websites. I searched for photo colorization, and I found a model called Colorizer that may work for what I need. Here is an example of the colorization I can get using this model. Here is another one. And here is another one. Really great. Let me show you how it works. The Colorizer model expects a black and white image as input. The Python source code I found converts any RGB image to a lab color space image. This color space has three channels. One represents the image lightness, or L channel, and the other two represent the color components. The color components are discarded, while the lightness becomes the input of the Colorizer model. The model then estimates two new color components that, combined with the input L channel, provide the resulting image with color. It's time now to make this model compatible with my app. To achieve this, I can convert the original PyTorch model to CoreML format using CoreML tools. Here is the simple Python script I used to convert the PyTorch model to CoreML. First, I import the PyTorch model architecture and weights. Then I trace the imported model. Finally, I convert the PyTorch model to CoreML and save it. Once the model is in the CoreML format, I need to verify that the conversion worked correctly. I can do that directly in Python again using CoreML tools. And this is easy. I import the image in RGB color space and convert it to lab color space. Then I separate the lightness from the color channels and discard them. I run the prediction using the CoreML model. And finally compose the input lightness with the estimated color components and convert to RGB. This allows me to verify that functionality of the converted model matches the functionality of the original PyTorch model. I call this stage model verification. However, there is another important check to be done. I need to understand if this model can run fast enough on my target device. So I will need to access the model on device and make sure it will provide the best user experience. The new CoreML performance report, available now in Xcode 14, performs a time-based analysis of a CoreML model. I just need to drag and drop the model into Xcode and create a performance report in a few seconds. Using this tool, I can see that estimated prediction time is almost 90 milliseconds on an iPad Pro with M1 and iPadOS 16. And this is perfect for my photo colorization app. If you want to know more about performance report in Xcode, I suggest you to watch this year's session, Optimize Your CoreML Usage. So, performance report can help you make an assessment of the model and make sure it provides the best on-device user experience. Now that I'm sure about functionality and performance of a model, let me integrate in my app. The integration process is identical to what I've done until now in Python, but this time I can do seamlessly in Swift using Xcode and all other tools you are familiar with. Remember, the model, now in CoreML format, expects a single channel image representing its likeness. So, similarly to what I did previously in Python, I need to convert any RGB input image to an image using the lab color space. I will write this transformation in multiple ways, directly in Swift with vimage or using Metal. Exploring deeper in the documentation, I found that the Core Image framework provides something that can help me with this. So let me show you how to achieve the RGB to lab conversion and run the prediction using the CoreML model. Here is the Swift code to extract the lightness from an RGB image and pass it to the CoreML model. First, I convert the RGB image into lab and extract the lightness. Then I convert lightness to a CG image and prepare the input for the CoreML model. Finally, I run the prediction. To extract the L channel from the input RGB image, I first convert the RGB image into a lab image using the new CI filter Convert RGB to Lab. The values of the lightness are set between 0 and 100. Then I multiply the lab image with a color matrix and discard the color channels and return the lightness to the color. Let's now analyze what happens at the output of the model. The CoreML model returns two ML-shaped arrays containing the estimated color components. So after the prediction, I convert the two ML-shaped arrays into CI images. Finally, I combine them with the model input lightness. This generates a new lab image that I convert to RGB and return it. To convert the two ML-shaped arrays into CI images, I first extract the value from each shaped array. Then I create two core images representing the two color channels and return them. To combine the lightness with the estimated color channel, I use a custom CI kernel that takes the three channels as input and returns a CI image. Then I use the new CI filter Convert Lab to RGB to convert the lab image to RGB and return it to the color. This is the source code for the custom CI kernel I use to combine the lightness with the two estimated color channels in a single CI image. For more information about the new CI filters to convert RGB images to lab images and vice versa, please refer to the session Display EDR Content with Core Image, Metal, and Swift UI. Now that I completed the integration of this ML feature in my app, let's see it in action. But wait, how will I colorize my old family photos in real time with my application? I could spend some time to digitize each of them and import them in my app. I think I have a better idea. What if I use my iPad camera to scan these photos and colorize them live? I think it will be really fun, and I have everything I need to accomplish this. But first, I have to solve a problem. My model needs 90 milliseconds to process an image. If I want to process a video, I will need something faster. For a smoother user experience, I'd like to run the device camera at least 30 fps. That means the camera will produce a frame about every 30 milliseconds. But since the model needs about 90 milliseconds to colorize a video frame, I'm going to lose 2 or 3 frames during each colorization. The total prediction time of a model is function of both its architecture as well as the compute unit's operation it gets mapped to. Looking at the performance report again, I noticed that my model has a total of 61 operations running on a combination of the neural engine and CPU. If I want a faster prediction time, I will have to change the model. I decided to experiment with the model's architecture and explore some alternatives that may be faster. However, a change in the architecture means I need to retrain the network. Apple offers different solutions that allows me to train machine learning model directly on my Mac. In my case, since the original model was developed in PyTorch, I decided to use the new PyTorch on Metal, so I can take advantage of the tremendous hardware acceleration provided by Apple Silicon. If you are interested in knowing more about the PyTorch accelerated with Metal, please check the session Accelerate Machine Learning with Metal. Because of this change, our journey needs to take a step back. After retraining, I will have to convert the result to CoreML format and run the verification again. This time, model integration consists of simply swapping the old model with the new one. After retraining a few candidate alternative models, I have verified one that will meet my requirements. Here it is with the corresponding performance report. It runs entirely on the neural engine and the prediction time is now around 60 milliseconds, which works for video. But performance report tells me only one aspect of the performance of my app. Indeed, after running my app, I notice immediately the colorization is not smooth as I expect. So, what happens in my app at runtime? In order to understand that, I can use the new CoreML template in Instruments. Analyzing the initial portion of the CoreML trace after loading the model, I noticed that the app accumulates predictions. And this is unexpected. Instead, I expect to have a single prediction per frame. Zooming in the trace and checking the very first predictions, I observe that the app requests a second CoreML prediction before the first one is finished. Here, the neural engine is still working on the first request, when the second is given to CoreML. Similarly, the third prediction starts while still processing the second one. Even after 4 predictions, the lag between the request and the execution is already about 20 milliseconds. Instead, I need to make sure that the new prediction starts only if the previous one is finished to avoid cascading these lags. While fixing this problem, I also found out that I accidentally set the camera frame rate to 60 fps instead of the desired 30 fps. After making sure that the apps process a new frame after the previous prediction completes and setting the camera frame rate to 30 fps, I can see that the CoreML dispatches correctly a single prediction to the Apple Neural Engine, and now the app runs smoothly. So, we reached the end of our journey. Let's test the app on my old family photos. Here are my black and white photos that I found in my basement. They capture some of the places in Italy I visited a long time ago. Here is a great photo of the Colosseum in Rome. The color of the walls and the sky are so realistic. Let's check this one. This is Castel del Monte in the south of Italy. Really nice. And this is my hometown, Grottaglie. Adding color to these images triggers so many memories. Notice that I'm applying the colorization only to the photo while keeping the rest of the scene black and white. Here, I'm taking advantage of the rectangle detection algorithm available in the Vision framework. Using VN detect rectangle request, I can isolate the photo in the scene and use it as input to the colorized model. And now, let me recap. During our journey, I explored the enormous amount of frameworks, APIs, and tools Apple provides to prepare, integrate, and evaluate machine learning functionality for your apps. I started this journey identifying a problem that required an open-source machine learning model to solve it. I found an open-source model with desired functionality and made it compatible with Apple platforms. I assessed the model performance directly on the device using the new performance report. I integrated the model in my app using the tools and the frameworks you are familiar with. I optimized the model using the new CoreML template in Instruments. With Apple tools and frameworks, I can take care of each phase of the development process directly on Apple devices and platforms, from data preparation, training, integration, and optimization. Today, we just scratched the surface of what you, the developer, can achieve with the frameworks and tools Apple provides you. Please refer to previous sessions linked to this for additional inspiring ideas to bring machine learning in your apps. Explore and try frameworks and tools, take advantage of the great synergy between software and hardware to accelerate your machine learning feature and enrich the user experience of your apps. Have a great WWDC and arrivederci!